It is 2:01. It's 2:01 UTC. 2:01. Somebody's late. Somebody's a little bit late. But hey, everybody, welcome again to Astronomy Daily Live. Coming at you live at 2:02 UTC. So hope everybody's doing well out there in the universe. Just got back. I was out and actually just got so just I should say just landed, right? Just landed and yeah. So I've actually had to rush just a little tiny bit, just a little tiny bit. Um, didn't didn't actually realize what time it was until I got home, and then it's like, oh. So yeah, hope everybody's doing well. Welcome again to today's version of Astronomy Daily Live. Hope everybody's doing well out there. Now, this is just a casual, fun, slanted get together. This camera is really acting a little, being a little obnoxious tonight. So let's see if I can fix that up in any way. Wow, it's really being sort of a weirdie tonight here. Let's see. Let's see if we can straighten her out a little bit. Wow, that's looking way over there. Hardware problems, hardware problems. There we go. Is that all right? That's a little slanted still too. Yeah, the camera's being a little funny tonight. It's not grabbing on like it normally does. But hey, everybody, hope everybody's doing well. I'm going to get that out of the way so my Linux machine doesn't freeze up like it will. And let's see what else. Hope everybody's doing well out there in the universe. Let's see. Oh, I've already got a big crowd. Tim, nice to see you in the chat. Bobby, hey. Uncle Bill, you were on time. You were on time. Somebody else wasn't. Let's see. Yep. Rush. What context? What context of Rush? You talking Rush the band, or just having to rush? Cheers. And yes, Uncle Bill, Rush is a four-letter word, and I avoid four-letter words if I can, for sure, especially those kind of four-letter words. All right, well, cool. So hope everybody's doing well. As I said, I just landed. I just landed. So let's just um, let's just go through archive.org and see what's new. See what's new. Archive.org. If you don't already know about archive.org and are interested in science uh, at all, right? Um, check out archive.org because this is where all the bleeding edge new science is going on. Now, it's not all of it, and uh, yeah, you may not get it all, right? But you're going to get quite a bit. And in particular, you're going to get astronomical news, new stuff. So as you can see, it's archive excuse me, with a capital X, right? That's a, a letter chi, a Greek letter chi. So they call it archive.org. That's pretty pretty clever there. So, but if you go to archive.org, you will see that there are papers, scientifically published papers, in journals or books or, anything like that. And you will see a lot of subjects, right? Now, rightly so, rightly in the right place is astrophysics, right? That's astronomy. That's a fancy term for astronomy. I prefer to call it astronomy as opposed to like astrophysics and all that. It's the same thing, and it just one sort of sounds a little bit more polished than the other. But I consider myself an astronomer. Um, and but I can also call myself a astrophysicist if I choose. It just I don't know. That's a big word. I'd much rather just say astronomer. That's astronomer. That's 4 syllables already, right? Astrophysicist. Let's see, astrophysicist. That's 5 syllables, right? That's just too much energy. That's too much. I'll stick to 4 syllables. I think it does the job really, really well. Anyway, that's on the top of the list, right where it should be, right? Because it's astronomy, should be at the top of the list. It is the best science, right? So, but as you can see, this covers all kinds of astronomy, right? And not only astronomy, but physics in general, right? And then all kinds of physics. So if you're interested in any of these kinds of things, uh, um, you know, click on any of these, right? And you'll find paper after paper after paper on exactly, what's what's being reported as new. Now, just I don't know if this really isn't inside information, but maybe it's something that you haven't thought of. And that is, when somebody publishes a paper, they move on, right? They move on. And it takes, you know, 3 or 4, 5 months, um, 6 months, a year, something like that to actually publish a paper. So by the time everybody else sees your paper, right, it's probably been at least a few months since you've even thought of any of that stuff, right? So what is currently being worked on, like right at this moment? Well, nobody really knows exactly, right? But we do know what the astronomers and the mathematicians, computer scientists, the biologists, the financial guys, the stats people, the electrical engineers, we know what they're publishing because, as I said, most of it is here. So yeah, I mean, if you want to get lost for a few hours, right, or a few days, go over to archive.org. Now, let me just point out a couple other. I mean, if you're into papers, right, if you're into reading this kind of stuff, which I greatly encourage. I mean, even if you're new to astronomy and or science, um, you know, try, try. And what I always say, right, is start with the pictures. Start with the pictures, read the captions, and go from there, right? I mean, you know, uh, this isn't a degrading thing, but when you were 2 and 3, right, you had picture books because that's all you could understand. Now, there's nothing wrong with that, right? I mean, science is about gaining understanding, gaining knowledge. And so, starting from a place where you don't know anything at all, right? That's exactly what every scientist does, right? I mean, that's the process of science. You have to start at the bottom and work your way up. And a lot of times that means just looking at the pictures and trying to understand them, right? then worry about the rest of the text, where they're trying to explain what they're doing and what they're observing and what their conclusions are and all that. That can come later, right? Look at lots of pictures, lots of plots. See what you can do with those. I mean, I there are so many people that say, "Oh, I can't possibly understand any of that because I'm no good at blah 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 blah." Well, I you know I mean, do what you're gonna do, right? I'm not saying that um, you know that is sort of the wrong approach. But if you want to get into astronomy, right, there's certain things that you're going to have to understand, and you're probably going to be wanting to understand them. So you got to dive in and start in the wading pool, right? Look at the pictures. Those pictures, a lot of them are, I mean, if nothing else, they're very beautiful, right? I mean, even if you don't understand what they're showing or anything else, look at them as an artistic piece, right? And that's it. Hey there, Patrick. Nice to see you in the chat. So let's go look and see what's sort of the bleeding edge here. I'm going to get my smartphone running also, so I can monitor the live stream, make sure that what I'm showing you is actually showing up. So this is the latest and greatest. So Archive is published every weekday, right? So Monday through Friday usually comes out around 1 hour UTC. So about an hour before I go live on the weekdays. Archive has Tim and Patrick are pairing up tonight in the chat to bring us um, uh, the signature piece of the chat. Thanks, guys. um, so yeah, this gets updated, as I said, around 1 hour UTC, and so yeah, I usually like to look at this, before the live stream. But as I said at the beginning, I just got home, and didn't even know what time it was. Something about me. I stopped wearing a watch when I was 14 years old, and haven't worn a watch since. So that's 35 years I've not worn a watch, and uh, you know uh, if I need to know what time it is, I can probably find out. I can probably find out, and um, um, uh, so yeah, I don't wear a watch. I don't pay attention to what time it is unless I have to, and sometimes I have to. So Tim is saying that they're modeling in Planet Nine to account for weird things happening. Yeah, Tim, uh, there are things in the so-called outer solar system that I think are going to blow our minds, and we're starting to see those kinds of things now. In that we're um, discovering more and more objects out there. They just came out with a catalog of like 850-ish um, trans-Neptunian objects, right? These are objects that orbit the sun outside of the orbit of Neptune, hence the name, right? Pluto is a trans-Neptunian object. And there's something like 800 of them now, and they can look at the orbits of these things, um, of these guys, and uh, from those orbits they can sort of infer that there's something interesting out there, and they think. that they know about where it is, and they know about how far away it is, and they're thinking lots of things, right? But let me tell you one thing that isn't mentioned a lot, and that is, in order to get a good orbit, the most important thing the most important thing that you need in order to get a good orbit is time. You need a lot of time. Okay? You can make as precise a measurement as to the position of that object as you possibly can. And you can do it every second, right? But these, especially these objects, right, these trans-Neptunian objects. Here, I'm going to flip back to my ugly mug, so you, because I'm going to be talking about this for a second, and I'm using my hand, and you're not seeing it. Um, so um, so these are, I'm still tilted. Look at that, man. These are trans-Neptunian objects. They have orbits around the sun that that are hundreds of years long, hundreds, thousands of years, right? Hundreds or thousands of years long, right? We've known about these objects for 5 years, 10 years, something like that, right? So let's just um, uh, let's just give everybody the benefit of the doubt, right? And and say a 200-year orbit. Okay, now that's for an object that we discovered 5 years ago, right? 5 years ago. So I'm going to grab the handy dandy Casio. What have I got? I've got a Casio FX 300 SA. And I've had this for, I want to say maybe a little bit more than 20 years now. I'm pretty sure. I'm pretty sure. I remember when I got this because it was my other calculator, which was almost exactly like this one. I'd had for about 15 years or so. So this one's actually outlasted that one as far as I know. As far as I know. Anyway, so 5 years into 200 years is 2.5%. Okay, so we've been observing this object for 2.5% of its orbit. Um, as I said, the most important thing in determining an orbit is time, because you have to be able to look at it, here and here and here and here and here and okay. Well, we've looked at you know this little tiny bit right here, right? And then we've made a fit, right? We've taken an ellipse, right? And we've, you know, um, uh, played with the parameters of that ellipse until the ellipse fit our data, our 2.5% of the full orbit, right? So, um, uh, so I'm just saying that we don't really have enough data really to be as accurate and precise as we want to be in terms of, you know, being able to figure out where this other object is. And yeah, Tim, if you're right, And I've heard those numbers too, 10,000 year orbit, 20,000 year orbit. Um, we've been looking at these things for just a few years, right? So we don't know the orbits very well. And since we don't know the orbits very well, knowing or, inferring that they're being perturbed is is sort of a stretch, is sort of a stretch. And then, okay, on top of that, saying, okay, if these are perturbed this way, then the perturbing object is over there, right? It's in this general area. And I'm just saying, you know, it's a stretch to be sure about these orbits, right? It's a pretty good stretch. Um, uh, it's also a stretch to take those orbits and say, okay, it's got to be over here. So those two things combined, mm, it's a real stretch. Are there things out there? Yeah, I wouldn't be surprised. I wouldn't be surprised. It's sort of like my answer to life, right? I mean, is there life out there other than on Earth? I'm not going to be surprised if there isn't. So, I mean, once we find it, and I think it'll sort of be like, yeah, 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 it was always there. And so I'm thinking the same thing about objects, way, way, way out there. Yeah, they're pretty small, they're pretty dark, and they're really far away. And that makes them extremely faint, extremely faint. And we just don't have the technology, right? We don't have the light buckets to be able to see these things. Now, LSST, right, the Large Synoptic Survey Telescope, um, is going to put a pretty big bite in that. Um, I think some interesting, well, I mean, it almost goes without saying, right? But I think some interesting things are going to be found out once we start looking, you know, very, very deep like that, and with a pretty high cadence, right? They're talking about the entire the entire visible sky from that location like every 2 days or so. So, I mean, it's going to be insane. They're talking about 10 million event alerts per day, right? 10 million something's going on up there every single day. It's going to be absolutely insane, right? Um, we very, very mistakenly thought for a very, very long time that things happen in space, but they happen really slowly. And once in a while you'll see a supernova going off in a distant galaxy and all of that, right? And it's like, the more we look, the more we find. And that's exactly what's going to happen here. LSST is going to I mean, remember the scene in Superman the movie when the dam breaks? All right. It's it's going to be absolutely insane. Um, Tim, this is not off topic whatsoever, because what this is a circle of friends talking about whatever, right? I mean, as long as it's astronomical, it's cool with me. So we're sitting around in our lounge chairs, right? With some kind of consumable. Cheers. Yeah, having a good time, having a good, fun conversation, all things astronomy, right? So no apologies, no apologies, no way, no way. I don't accept apologies like that. um, So yeah, let's go back on to um, archive.org though, and just sort of see what's going on there. Um, my my only main point there, Tim, is is that definitely don't accept everything that you hear. Um, what I do, and I say this almost every live stream, right? Is that I'm extremely skeptical and I'm extremely open-minded. So I love I'm crazy about all of this, right? I think it's extremely exciting, and I want all of that, right? I want everything that we can possibly imagine. Uh, I want to happen, and I want everything that we can't imagine. That's especially awesome, right? But at the same time, it's like, well, you know, bring me the proof. Show me how you're going to do it. And then, you know, go get the data, right? Get the data and then bring it back and make sure that that data is good data, right? Because it it's the principle of garbage in, garbage out, right? So if you put in crap into your models or or your theories, right? It's all you're going to get out is a different kind of crap, and so that doesn't do anybody any good at all. Make sure that the quality of your data that is going in is the best that you can possibly make it. Okay, don't mess around there, right? And then run it through all your mills, right? And out the other end should come something pretty interesting and pretty reasonable. So those are the two things that I always keep in mind. So all right, let's go over to archive and just you know this is what I do. This is just what I do. I start at the top and I start reading titles. Yeah, you try to think out what we're told. Yeah, yeah. The other thing too, just as another quick aside, okay, as an astronomer, okay, who knows a few things, right? I can tell you that as far as the media goes, like television, radio, those kinds of things, uh, when I hear an astronomical story, okay, 90% of the time there's something wrong with what they say. Now it's usually not the case that they're like, making something up, right? They're not lying, but what they're saying isn't isn't right isn't right. They've confused things. So that's I sort of extrapolate that out, and then say, okay, well, if they're confusing things about a topic that I know about, are they confusing things about other kinds of topics that I don't know anything about? Well, probably they are. So that's one of the reasons why I don't really listen to the news anyway. So, but I don't know how I got off on that. Anyway, so what I do is I just look at the titles and see if there's anything that sort of flashes in my head. So, um, if you see anything here that looks particularly interesting, let me know. I mean, I'm the host, so I mean, you have to let me know if there's anything sort of that tickles the back of your head in any way. Um, let's see, testing the equation of state of neutron stars with electromagnetic observations. Electromagnetic observations, isn't that just light? I'm not quite sure. Um, yeah. All right, we're gonna move on from there. Calibrating long period variables of standard candles with machine learning. Now, the idea there is they've and they've done this actually with a number of different kinds of variable stars. What we've apparently observed, right, is that a certain kind of variable star uh, uh, will have certain characteristics, right? It'll have a period of variability, say, and um, how much the variability actually takes place, right? So if a star is getting bright and dim like that, well, how much does it brighten? How much does it dim? And then how long does it take? Between um, two brights, say. And we can look around in the sky and find that there are a bunch of these kinds of stars, right? And there are different types, right? Um, and well, it turns out that all of these stars seem to sort of be the same brightness as well, right? And if and furthermore, they have found that um, that there seems to be a relationship between how bright they are and their variability period. So uh, if that's a known quantity, you can use those as what's called a standard candle, right? And that is, use the example of a candle, right? Um, if a candle is next to you, you can measure its brightness, right? And you can know how far away it is, right? And then you can move that candle trillions of miles away, right? Thousands of miles away, whatever, right? Measure its brightness again, and some simple math, right? Its geometry will tell you um, uh, how far away that object is just by knowing how bright it is, right? It's the 1/r² law. So um, apparently we've been able to do this with variable stars because we've seen that there's a relationship between their period, and that's the time between brightnesses. So it goes from bright to dim, back to bright. Well, that period of time, there's a relationship between that and how intrinsically bright they are, and so if we can uh, look around in the sky and find variable stars that are like this, then we can sort of infer that, okay, that star has this intrinsic brightness. And if it has this intrinsic brightness, then it must be this far away. So that's sort of what that's all about, right? Not even going to get into the paper. It's just an interesting topic. But they're using machine learning um, to do this, which is cool. I, you know, maybe this is tangent night, but I'm a little confused as to why neural nets and machine learning hasn't really progressed very much. I mean, I I wrote my first um, neural net 20 years ago, right? When we were getting into adaptive optics, one of the ways that we thought that um, tr- we could actually train a system to do the adaptive optics for us, right? And so I wrote some code that actually trained a neural net, and I look at the neural net stuff and the machine learning stuff now, and it doesn't seem like it's changed very much. I don't know. I'm not into it probably as much as I should be in order to have a valid opinion there. So, hmm. So reversals in the direction of polarization rotation in some object, OJ 287. So we've obtained a smooth time series for the electric vector position angle of the blazar OJ 287 at centimeter wavelengths by making plus or minus n times pi adjustments to archival values from 1974 to 2016. The data display rotation reversals in which the EVPA rotates counterclockwise for 180 degrees and then rotates clockwise by a similar amount. Time scale of the rotations is a few weeks to a year, and the scale for a double rotation, including the reversal, is 1 to 3 years. We've seen 4 of these events in 40 years. A model consisting of 2 successive outbursts in polarized flux density, the electric vector position angle, counter-rotating, superposed on a steady polarized jet, can explain many of the details of observations. Wow, okay. That's pretty heavy. That's pretty heavy. Yes, I did record today's Hearts of Space. I have not listened to it yet. I didn't get around to that today, but I think it's going to be an interesting one. I was looking at the title. It's as far as I got. What's the title say, Bobby? Dun, 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 dun. The title says, I'm going to go to this week, Inner Rhythms. Inner Rhythms. So, yeah, kind of interested in seeing what that's all about. They're talking about the trance rhythms of the Middle East, Asia, and Africa. So, kind of interesting. Let's see, James Hood, Brian Metcalf, Lauren Narrell, Dream Jungle, another Byron Metcalf, Don Lee, 2 from Don Lee. I don't recognize any of those names, Bobby, at all. But yeah, it looks kind of interesting. I'm definitely into rhythm. So yeah, kind of interested in seeing what that sounds like. As I said, I've got it recorded. I just need to listen to it. So that seems like a pretty heavy article. Okay, so here's an interesting one, right? They're just looking at an asteroid, just an asteroid. 3634 Iwan. So this is kind of interesting. This is from the Bulgarian National Astronomical Observatory. Pretty cool. Cheers to Bulgaria observing asteroids. Asteroid was observed only one night on the 22nd of March 2017, accidentally. What? Accidentally in the field of view in which our target for shape modeling, asteroid 289 Nanetta, was positioned. Oh, that's very cool. That's very cool. Let's see, the asteroid light curve database did not contain any previously reported results for 3634 Iwan. If we accept that the light curve of the asteroid is typical with 2 maxima and minima, a single night observation covers the whole rotation cycle. Interesting. So the light curve plotted by the minor planet MPO. I don't know what MPO is. Interesting, Uncle Bill. Just read your comment there. His work. Yeah. Oh, yeah. There's Uncle Bill. There's a cavern, a cavernous abyss between neural net, machine learning, and AI. Oh yeah, there's a huge. I mean, I would say that's almost not the same, not the same at all. Yeah, I think AIs are probably going to use neural nets to learn things. But that's about it. Yeah. Um, anyways, this is kind of interesting. So, they sort of stumbled upon it accidentally. Accidentally. That's kind of funny. And they only took one night's worth of data, right? Because they were interested in something else. Our assessment is that for the uniqueness of the period solution, we need longer observational span, which will reveal the number of extrema of the light curve and confirm the quality code U equals 3. Okay. Well, that's a candidate. That's a candidate. Fast coherent direct imaging on ground based. Okay. All right. Self coherent camera. That's getting into adaptive optics. Cool. Morphology and kinematics of orbital components of Khalifa galaxies. I don't know what a Khalifa galaxy is. It's probably a survey of some sort. Implications for small spin changes measured for large Jupiter family comet nuclei. Okay. Seeing that the spins of comet nuclei are changing, huh? These guys have measured the distances to these NGC objects. Okay, cool. I wonder what kind of objects these are. Um, looks like galaxies. Yeah, looks like some galaxies. Tim, take care. Enjoy the hay. Don't fall over when from passing out because you're exhausted walking the neighbor's dog. Make it a short walk, maybe. But thanks for coming in, Tim. Thanks for the tangent. I love tangents as long as they're relevant, right? Take care, Tim. Direct imaging of the HD 35841 debris disk. Cool. How'd they do that? From the Gemini Planet Imager in H band. Highly inclined ring of debris. Very cool. Down to a projected separation of 12 AU. Very cool. Always fun to see those kinds of advances. Our resolution is just going to be getting better and better and better. Strengths on the distance moduli, helium and metal abundances, and ages of globular clusters. Phew, serious work there. The nature of the Stingray Nebula. Stingray Nebula, huh? Looking in the radio, of course. Analyzed the full suite of Australian telescope compact array data from the Stingray Planetary Nebula. Data taken, blah, 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 blah. The radio flux density of the nebula generally declined during that period, but between 2013 and 2016 just shows signs of halting that decline. Okay, so it was getting fainter and fainter and fainter. We produced the first spatially resolved radio images of the Stingray Nebula from data taken in 2005. A ring structure associated with the ring seen in the HST images. Cool. The Stingray Nebula, huh? That's pretty nice. Let's see. Anything else look interesting here? There's usually 20 or 30 articles, so we just gotta get through some of them here. Out too many tangents. Although I love the tangents. A new interpretation of Sierkowski's polarization law. I have no idea what that is. Basic tenets of the alternative interpretation to be presented here are that the spectral profiles of the starlight polarization peaks observed in the visible and near IR are a result of the optical properties of silicate grains in the same spectral range, not of the grain size, provided it um, provided it remains within the range of Rayleigh's approximation. Okay. Yeah, here are actually two of the known standard candles, the Cepheid variables and the RR Lyrae variables. Cepheid and RR Lyrae variables as standard candles, and what else? What else can they be used for other than just being standard candles? So light curve analysis and pulsation properties of these rapidly pulsating stars provide stringent tests for theoretical evolution and pulsation models. I discuss a detailed light curve analysis of classical Cepheid variables in the galaxy and the Magellanic Clouds at multiple wavelengths. The variation of light curve parameters as a function of period, wavelength, and metallicity is quantified to constrain the theoretical parameters, such as mass luminosity relations obeyed by Cepheids. That's pretty cool. Short, short one too, just 5 pages long. Pretty awesome. Photon index correlation, the Gaia ESO survey, scalable platform for adaptive optics real-time control. I'm gonna have to look at that one. Novel architecture for adaptive optics control based on FPGAs, making active use of their configurable parallel processing capabilities. Cool. Yeah, that's one of the big things in adaptive optics is that you have to have a fast system. You have to be able to uh, sample your data, right? Collect your data, and then process it and calculate um, how you're going to adapt your optics. And then you have to move your optics, right? And you have to do this on a time scale that is, um, at least equal to, if not faster than, sort of how fast the atmosphere is moving, right? Now, all of you, I'm sure, have seen, um, uh, um, the shimmering of starlight, or you've seen, on a hot day, you sort of look out and you see a mirage, right, along the horizon there, right? And look and see how fast that's moving, right? We have to have adaptive optics systems that move faster than that, right? So anything to make it go faster is a plus. So they're talking about, let's see, yeah, for this, yeah, for regular wavefront sensors, the reconstruction takes between 39.4 microseconds up to 1.283 milliseconds or so. For large 1 millisecond, Um, yeah, they don't talk. They don't say in the abstract how fast they're going, but they're probably going at least that fast. They have to. Java package for astronomy with 12 years of development and use. JParsec to compute ephemerides. Cool. An ephemeris, right, is just the position of an object uh, over a particular time period, right? And it's the position of that object in the sky. Something about Tess. Here, Tess is doing pretty well up there so far. Can't wait to see some more images. That first one was pretty nice looking, pretty encouraging. Abundance of zinc in the red giants of galactic globular cluster 47 Tucanae. That globular is one of the big ones that we can see. Variable binaries and variables in binaries. Uh-oh. You know what? I'm being summoned. I'm being summoned to be doorman here. So I will be back in like 10 seconds. Hold on. All right, that was a little bit longer than 10 seconds. Let's see. So blah, 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 blah. Let's see. That's the analysis for magic telescope data. The increase in sensitivity of imaging atmospheric Cherenkov telescopes. Never heard of that. Has led to numerous detections of extended gamma ray sources at um, um, I don't know, tera electron volts. I don't think I've got those units right. Huh, interesting. Okay. Galaxy Cluster Mass Reconstruction Project. Am I seeing anything incredibly interesting here? Got to look at something. All right. Well, let's go back to that first one. Don't even remember what it was now. Quite a few articles. There's the asteroid, but wasn't there one? Oh yeah, reversal and direction of polarization. Let's let's look at this one instead. Let's look at the asteroid one. Is that all right? All hail the feline overlords. Pizza guy's here. All right, let's see. As I said, first thing to do is let's look for some pictures. I like looking at pictures, especially with the live stream, right? I mean, it's a little bit easier than just reading through things and all that kind of stuff. So I'm going to zoom out one little thing here. Here's some plots. So here's the relative light curve of this asteroid on the 22nd of March 2017. And Hmm. So it looks like what they've done, right, is they've measured the difference in brightnesses between the asteroid and some stars, right? They've taken two stars in the field of view, and they're calling those M4 and M5, right? M4 and M5. And what they've done is they've looked at the difference in magnitude between M4 and M5 and the asteroid in M4, right? So the the idea here, right, is that if the difference between M4 and M5 is pretty constant, then that probably means that M4, the actual magnitude of star number 4, is constant as well, right? Now, the only other way that this difference could be exactly the same is if these two magnitudes were varying, right? Were changing over time exactly at the same time, exactly in the same way. And that's unlikely, right? So the fact that they're seeing a pretty constant difference in magnitude here, yeah, I can buy that for sure. So that means that M4, that the actual magnitude of star um, number 4 is probably constant too. So if you're seeing any variability between the brightness of the asteroid and star M4, you have to conclude that it's the asteroid that is making that kind of difference in magnitude. And yeah, look at that. That's a pretty complicated light curve. But you know what? I think a lot of asteroids are like that, right? Because I mean, asteroids aren't necessarily rotating; they're tumbling, right? So they have they have up to three different axes of rotation, right? And uh, you know they could all be 90 degrees to one another, right? So who knows, right? Yeah, I think that is absolutely sweet that their actual you know uh, target was something else, and it just so happened. Yeah, they're saying here that in the field of view for about 6.5 hours um, uh, was seen this other target. Um, okay, pretty near to um, opposition as well. So that's probably why. Well, that's totally why it was as bright as it was to be able to actually be observed at all. Because at opposition, that's about as close to us as it's going to get. So that is very very cool. Okay, so yeah, again they compared the brightness of the asteroid to a few other stars, and yeah, more or less got the same curve, right? Makes sense. So this is a six-order fit using Fourier analysis. So yeah, I've got to agree with them that I don't think they're seeing the whole. I don't think they're seeing the whole thing. That's a pretty good fit, right? Um, but yeah, I would say, well, I don't know. You see here how there's a high point and sort of a high point, and then here there's a high point and a high point. So I'm sort of wondering if that's what they're sort of going by, because they're saying 4.72 hours, right? 4.72 hours, 4.72 divided by 24. Come on. That's like point 2 days, right? So, oh, point 0.2. Yeah, I don't know how they're getting that period, because I mean, I'm seeing something here, right? Here to here is one period, and that's almost half a day. So, yeah, I don't know. Yeah, I'm not yeah, a phase plot for 4.72 hours shows the inequality of the two halves. Yeah. Yeah, yeah, I'm not seeing any I'm not seeing anything there, right? Yeah, see where I'm not sure. This is a period spectrum. It's sort of like a Fourier transform, showing the frequencies that pop up in this data. And yeah, I guess they're seeing a peak at 4 point. I I don't know. I'm not quite understanding where they're getting 4.72 when I definitely see a peak at almost 4 and I see a peak at almost 6, right? Yeah, I'm gonna have to really question this one, because I think it looks like I don't know, they seem to be pretty way off. Ooh, yeah, that's just nasty looking. Yeah, I mean, it's exactly the same thing that I just said, right? In order to get good good data of this kind, you need time. You need time more than anything else. Yeah. Um, okay. So yeah, they they didn't. At least I didn't see anything. Let's go back now. Now that we've sort of looked at all the pictures, and see if they give like an orbital period around the sun. And how close does it get? Um, Okay, yeah. So the opposition was on March 11th, so that just happened. Um, and asteroid 3634 was magnitude 16.7 at the time, 270-second exposure. See if we can find out any more about. Okay, here we go. It's a main belt asteroid, orbits the sun for a period of 3.36 years. So yeah, the closest it's going to get to us is about what, 2 astronomical units. I think. I think. Well, I'm not gonna. I don't remember what these symbols mean. What 1.38 means. Not quite sure about that. So, but anyway, it's got it's got a period of 3.36 years, which puts it in um, the main belt. sort of nearby main belt, but definitely outside the orbit of Mars, right? Definitely outside the orbit of Mars. So, the closest it's going to get to us is, yeah, about 2 astronomical units or so. So, yeah, it's got to be pretty big in order to even see, right? Let's see, anything else interesting about this asteroid? Doesn't look like there's anything too interesting about this, just that, yeah, I mean, it should be looked at a little bit more. It brings researchers close to understanding past and present processes of our planetary system. Due to the huge number of asteroids and limited opportunities to visit them by spacecraft for a detailed study, information about morphology and dynamic characteristics of asteroids are obtained from ground-based telescopes. Yep, photometry. Photometry is the first thing to do. Just look and see what you can see. Yeah, very cool. Schmidt telescope. That's pretty cool. Yeah, I don't see anything else particularly interesting about this guy. Just wow, what an amazing thing to sort of stumble on, right? That's got to be a little surprising. See, what does they say? They try to calculate. Okay, yeah, yeah. I think they don't have enough data to calculate anything. That 4.72 hour thing. Nah. I'm not going to buy that one. No, I mean, I look at this and it's like 7.2 or 4.7 hour thing. That's zero point 0.2 of a day, right? Where do you see a periodicity there? I don't know. I don't know. Sometimes these things I just don't buy. So, but pretty cool, pretty interesting. This kind of a discovery, um, something that they didn't plan, um, but additional observations from additional nights. Yeah, probably gonna, and as they say here, they might have to wait um, for the next opposition when it is bright enough to actually see. Because I mean, by now, right? I mean, it's June, right? If opposition happened in March, they said, in March 11th, something like that. And they observed it really, really near opposition, so it's probably about as bright as it's going to get, right? So okay, they observed it on the 22nd of March. It was at opposition on March 11th, right? So that. Wow, that's lucky. That's just lucky. But by now, I mean, if it was 16.7 at its brightest, right? It's got to be really faint by now. Probably not. Can't be seen. But yeah, I'll. It'd be interesting to take a look at that um, and see when it's next going to be close. I've got a means to do that. Maybe I will. Maybe I won't. All right. Well, as always, there's always pretty amazing things, new and amazing things going on. Not only, of course, in astronomy, but everywhere. It just blows my mind, right? It's just like, wow, what what an amazing place we're in. What an amazing time we're in. not really any more amazing than any other time, but pretty cool nonetheless. Pretty cool nonetheless. And to have access, to these papers and find out what's going on is awesome. Is very, very awesome. All right. Well, I'm going to leave it at that for tonight. Cheers. And I am going to get out of here for today. So I will check you guys out again tomorrow, 2 hours UTC. So a little less than 23 hours from now, right? So don't get dizzy, right? We are on a spinning sphere. So, hold on to your hats and it's a pretty smooth ride though. So don't have to worry too much. But I will see you on the spin tomorrow. All right. Take care, everybody. Bye.